Hi and welcome back to my channel, Chem-MrT or Chem-MrT. So we're looking today, topic 6, rates of reaction and equilibrium or reversible reactions, and combining the two in something called the Haber process. I'm going to be looking at something called compromise conditions in a reaction. So we're going to learn about the Haber process, what it is, why it's so important for humanity in general. I'm not exaggerating with that. It genuinely is vital for the society we have, and without it we would not have the life that we have now. The world would be a hugely different place. We're going to look at the conditions the reaction's done in and why these conditions are a compromise. They are not necessarily the ideal ones for either the rate of reaction or the amount of yield that we want to get. So, the Haber process, what is it? It's a method for making ammonia from nitrogen and hydrogen. Now, ammonia is incredibly important for fertilizer, also important for explosives, and this made a big deal in World War I. But the reason why it's so important is because of the fertilizer. Without the fertilizer that is made from this process, we would not be able to feed the world's population, certainly not in highly densely populated countries like the UK. There just wouldn't be enough food that we could grow, certainly not without turning almost all the land into farmland. And when you think about that, then we wouldn't have anywhere to live. We'd all have to live in high-rise buildings, in very, very dense situations, which would make coronavirus even more deadly. So prior to the development of this process, it was very difficult to make ammonia. A lot of it came from natural resources, so guano, so bird poo essentially, was a very rich resource of it. But it was very difficult to make in a lab. So it was made from nitrogen, which was easily obtainable from air, which is a really, really useful thing. Nitrogen makes up 78% of the air around us, so it's a huge resource we can tap into. So that makes it highly desirable. And it was developed by a guy called Fritz Haber, hence the name. And there's quite an interesting story of his life, and I may do a video of his personally another time. Now, the reaction takes nitrogen and hydrogen. Nitrogen we get from the air, hydrogen we get from natural gas, so methane, and breaking that down through a fairly simple chemical process. And it makes ammonia, and it's a reversible reaction. Now, nitrogen and hydrogen, you should know, both are diatomic molecules because they're gases that exist in nature. So all the gases that exist in nature, apart from methane, and which is CH4, but all the elemental gases are diatomic except for the noble gases, so the group 0, group 8. So we get N2 gas plus 3 hydrogens gas H2. And reversible reaction, it makes NH3, which is ammonia, 2 lots of that, and that's also a gas. We use iron as a catalyst, which speeds up the reaction, which we know from rates. However, it speeds up both the forward and the backwards reactions equally. So whereas we use it to make this reaction happen, we use it to lower the activation energy essentially. It's not going to make more ammonia. It will make the amount of ammonia that we get slightly quicker, but it will also make the ammonia break down into the nitrogen and the hydrogen quicker. But it does lower the activation energy, and if we lower the activation energy, we lower the amount of energy required to start the reaction, which is obviously beneficial to industry. This isn't a compromise though. Now, one thing to notice is the forward reaction, so taking the nitrogen and the hydrogen to make the ammonia, that is exothermic, so it gives out heat. Reverse reaction is obviously going to be endothermic. Now, put the video on pause and have a little think about what reaction conditions would you use to maximize the rate using your knowledge about rates, which we've covered in previous lessons, and what conditions would you use to maximize the yield. So count the number of molecules of gas on each side, think about the fact the forward reaction is exothermic, the reverse reaction is endothermic. What would you use? So put the video on pause now and come up with some answers of your own, and we'll have a look through them in a minute. So, the first compromise condition is temperature. Now, the forward reaction is exothermic. Therefore, to increase the yield, we'd want to keep that temperature low. The lower the temperature would favour the forward reaction because we're keeping the temperature low, and therefore the equilibrium would shift to the right. If we keep that temperature low, we'd produce more ammonia. However, this slows down the rate of reaction. The reaction has a very high activation energy, and in fact if you keep the temperature low, the forward reaction won't happen at all. You need to give it enough energy to start that forward reaction, so it's quite a difficult compromise to achieve. If we make a slow rate going forwards, that means not much product is going to be made, and if you're doing this on an industrial scale, that means not much profit, so it's not worth doing. The solution is we use a compromise temperature of 450 degrees, which seems quite hot, and for humans it certainly is, but on an industrial chemical reaction scale it's probably about a middling temperature. So we use that because it allows the product to be produced at a reasonable rate. It's above the activation energy. We are going to make some of the product, however it's going to leave quite a lot of the reactant unchanged, so we're going to have a small percentage of our ammonia and we're going to have a high percentage of our nitrogen and hydrogen. But it's a compromise. If we were to lower the temperature, whereas we might have more ammonia, it's going to take us a lot longer to produce, which isn't so good. Now, pressure. The product side has fewer molecules of gas than the reactant, so the ammonia, we've got 2 molecules of that compared to the 4 molecules on the reactant side, reactant side. So higher pressure makes more ammonia, which is a good thing. So the reaction is done at high pressure. Higher pressure also equals a faster rate because you're crushing those reactant particles closer together, so they're more likely to collide and more likely to react. So a high pressure of 200 atmospheres is used, but we don't use higher because the higher the pressure, as you start to go up higher in pressure, you start to increase the risk of accidents, things like explosions or gas leaks and things like that. So a little bit like you may have seen demonstrations where you can fill a glass tube with a tiny little bit of water and then seal it and then heat it up over a Bunsen flame. As you do that, the water starts to boil and the pressure inside starts to increase to the point where the glass fails and the glass explodes. It's called a Krakatoa tube. You can, like the volcano, you can look it up on YouTube. There's loads of really good videos of those. Another problem with using really high pressure is as you start to increase the pressure higher and higher, you have to make your reaction equipment stronger to deal with those kind of pressures, and that makes it expensive. So we use a compromise value of 200 atmospheres of pressure to balance our desire for an increased rate and an increased yield with the cost of making the equipment for that. Now there are a few problems in the Haber process. We'd like to reduce the concentration of ammonia in the reaction vessel because if you remember from Le Chatelier's principle, if we reduce the concentration of our product, of what's on the right hand side, the position of the equilibrium will shift and it will use up more of our reactants to make more ammonia. The question is how? The reactants and the products are all gases, so nitrogen gas, hydrogen gas, ammonia gas. That means they're very, very difficult to separate. It's very, very difficult to separate gases. You imagine air around us is a mixture of gases. If I asked you to separate the oxygen away from the nitrogen, you'd find it impossible to do without certainly some specialist equipment. And the specialist equipment really is cooling it. Okay, so if we take some of the equilibrium mixture out, we take it away from the reaction vessel and then cool it down, what happens is the ammonia condenses and forms a liquid ammonia, so liquid ammonia, but the nitrogen and hydrogen don't, and they don't because their boiling point is significantly lower than ammonia's. So it means the ammonia condenses, the nitrogen and hydrogen stay as a gas. When the ammonia is turned into a gas, we can open up a liquid. We can open up a tap and drain the ammonia off. This reduces the concentration and means the equilibrium is going to shift and produce more ammonia. So win-win. It also means that we can then take the nitrogen and hydrogen that is not reacted and recycle it back into the reaction, which again is going to increase our yield, is going to increase our efficiency and increase our profits. And this is a diagram of a reaction vessel. Now apologies that it's not the clearest, it's a photocopy from an old worksheet. Into the side we pump in our nitrogen and hydrogen in the 3:1 ratio that we need for the reaction. The hydrogen and nitrogen mixture flows into the reactor vessel. It's hot at this point, flows into the reactor vessel, and we've got iron catalysts, so trays of it. So basically iron sticking out with powdered iron in there to act as a catalyst, and it forces the gas to move in a zigzag pattern. And again, high temperature 450, high pressure 200 atmospheres, and some of it turns into ammonia. So in the bottom here we have a mixture of hydrogen, nitrogen and ammonia, but we've got a condenser which is going to cool all this down, and it means that the ammonia gas condenses, turns into a liquid, and we can tap that off. The hydrogen and the nitrogen that have not reacted then get pumped back up and recycled, and so this process can carry on and carry on. We're still removing the liquefied ammonia, which is going to push the equilibrium further to the right to make more ammonia and improve our yield. So a little summary then of the Haber process and the whole point about compromise conditions. So in industry there's almost always a need to compromise between rate, yield and profit, and in the exam you may be asked questions about explain the effect of increasing temperature or pressure on a given reaction. It might not be the Haber process, they could pick any reaction, so that I can't cover every reaction that there is because they have an infinite choice on that. So you need to learn the principles here. We can use our knowledge of Le Chatelier's principle to predict the conditions that are going to favour having a high yield. We can also use our knowledge of rates to predict the conditions that are going to favour a faster rate. If the two are the same, like it was for pressure in the Haber process, then great, we keep high pressure. If they're opposing, like temperature, then we need to find a compromise. Financial and safety considerations also need to be taken into account and may make a difference to the reaction. Okay, so that's a very quick video on the Haber process, and more particular how in chemical reactions we often have to use compromises to make enough product in enough time to make it financially viable. If you want to think or look into some more of the safety considerations that might need to be taken into account, I suggest you look up an incident which happened in India called the Bhopal, I think it's Bhopal, the Bhopal accident, which was basically where people were skimping on the safety to try and make more profit, and the horrific consequences that caused. In my opinion, you've probably heard of Chernobyl and the accident there. Bhopal chemical accident was far worse in terms of the damage it did to humans and the environment, but because it wasn't nuclear, it doesn't get the same kind of fear and notoriety that Chernobyl gets. So look that up. Anyway, I hope that you found this video useful. If you have, please remember to give it a like. Please remember to subscribe as well and share the video. If you've got any questions, leave them in the comment section below, and I look forward to seeing you in a future video. Okay, bye bye.